second part of the video, I'll be explaining shear loading. As I'm not in front of you, it is a little bit hard to explain this thing, what is shear loading. So I have made a line diagram. Take a case of cantilever beam. In this case, we have a load F applied on the beam. If we calculate reaction, we will be having reaction F and bending moment reaction of M is equal to F. This thing I have already explained you in the class. Uh, if we have two bolts attached at distance d, this torque M, which is equal to F into L, can be obtained by resisting P from one bolt and P from bottom bolt. So a total of P into D or Pf into L will be the total torque. So in this case, this torque M, resistive torque M, will be resisted by two bolts of which will be applying load P at this point, and second bolt will be applying load P at this point. One bolt will be applying this load in compression and second bolt will be resisting in tension. This we have already studied. What physically what it be like? Say we have four bolts, two bolts on the top and two bolts on the bottom. So if we have two bolts, force on one bolt will be F and force on two bolt will be 2F. This 2F will be equal to P. Exactly same case. This load, this red thing, think as supporting wall or supporting block. We have one bolt here, one bolt here. Distance is D, so we can just calculate from this external moment, which is equal to P into D or F into L in this case, which as it has to be equal to this value, and the final force of bolt comes out to be M divided by 2 into D. And this M is equal to F into L. It depends on length and external load. So to support this load, we should have a bolt supporting load equal to this amount. And how to support load, that we have already studied in the previous sections. Now see this, so this is exactly same thing. This is a figure that load FB instead of P, this is load FB, and the remaining theory is exactly same. But on the second hand, if you see the figure from here, there are two bolts here and two bolts here. You will get a final figure like this. This is the beam which comes out of the paper. Load is applied vertically downward, and there are four bolts supporting 1, 2, 3, and 4. There are 4 bolts supporting this frame with the wall. This F is resisted by these 4 bolts. So at the end, we will get a 4 F by 4 equal distribution of load. F by 4 load will be acting on each bolt. These will be the loads because this is the reaction force to this F, and these bolts are reacting to this external force. So these will be the resistive forces applied by the bolt on the cantilever beam. But as every action has equal and opposite reaction, these are the reactions. Action is this load. These F by 4 forces, red forces, force applied on bolt. This external force has 4 components. One component is applied on each of the bolt. F by 4, F by 4, F by 4, and F by 4. So you just need to understand that if there is a reaction, we can just calculate reaction by calculating applying equilibrium equation. These will be the reaction exerted by the bolts on the assembly. But to calculate failure of bolt, we are concerned with these load which are applied on the bolts. These are same in magnitude but opposite in direction. So this is a simple description of what is shear load. Now there are different types of shear load. This is simplest example of shear loading. There we have this theory can be applied on rivets as well. So bolts or rivets, it's exactly the same thing. Bolts in shear are exactly same as rivets. So this is a case of shear. Bending in rivets, if because there is a distance between these two forces, This is the distance between this force and this force, this distance T. If you say that total thickness of this joint is equal to T, then half of this T, almost half of T, it will create a couple. So this couple will cause a bending. So these are, I will explain one by one in detail. This is simple bending of rivet. M is equal to this if this is T by 2, because it is acting exactly at the center. Uh, Point load, if for load is distributed, the average load or the sum of load will be acting at the center. Similarly, sum of load will be acting at the center. So it moment arm will be T by 2. So this will be the moment arm. Uh, F is the force, that this force is F, which is applied on the rivet. If you need to calculate, we can calculate sigma, which is equal to MC by I, or M divided by I by C, and I by C is the property, dimensional property, is a geometric property. It does not depend on the material. So I by C is the section modulus of the weakest member. So wherever we have the uh, because M is same throughout, we will calculate where is the weakest, where will be the weakest member. We will calculate sigma for that member. Sigma for weakest member, this value will be highest, so our stresses will be high. You see, we have studied this thing in detail when we studied in MOM 1 bending moment. Shear and rivet. There is possibility that due to this load, the rivet fail in shear or bolt fails in shear. So for that, we have force divided by area. And what is the area? This is the area. And usually the bolts are round. So this area is calculated by pi by 4 d square. This area, pi by 4 d square in case of rivet or bolt. There is a possibility that the members fail in tension, because when we apply load, this cross section, if we take this cross section, this will be in tension. But this member has smallest area here, because this area minus 2 holes is the cross section area here. So it is possible that these members fail in due to tension in this area. You know, you can just calculate area. What is the area? Area of this rectangle minus 2 holes, and not circular holes, because the cross section area is rectangular. Holes are in this area, holes are like this. You need to calculate this thickness and this dia. So you have rectangular area here, rectangular area here. So the final area will be, I have not written the equation, the final area will be equal to this. If you know, if you have value of this equal to W, so the total area is equal to W into this thickness, W into T, minus D into T, minus D into T, or W minus 2D into will be the area in this case. There is a possibility that the rivets or member or bolts are fail in bearing. What is bearing? It is just like take an example of foam. If you put something on foam, it compresses. It is compressed. That is, the load is applied exceeding its bearing strength. The foam does not fail, but metals, if they deform once, they are failed. So exactly similar, exactly in the same manner, if a load is applied in such a way that the material of member deforms, compresses, or the bolt material of bolt compresses, this is the bearing. And what is the area of, again the value is same, force divided by area, but crushing of the rivet, you can just use a term as well, crushing of rivet or compression of the component. The area can be calculated. If you go into right theory, you have the area is this circular portion divided by, multiplied by the thickness, which is equal to T. But as the load is not uniformly distributed, we can just say that area is equal to this D multiplied by this thickness. So this is the area, D into T. In this case, area is equal to D into T, where T is the thickness of this plate. Sorry, it was written here already. Tensile and shear tear out. Because just see the picture. If we have, if don't we, it is, if this is a plate and we, this distance is very less, and if you apply load, it is possible that the material tears out from this portion. And similarly, it is possible that the there is possibility that the material also, either it can shear or it can be tear down, or it can be shared. It is exactly same like you put some paper in clipboard, and if you apply force, if the distance is small, the hole can be enlarged and it can break the uh, paper. Paper can be tear down. So it, either this or this, these failure can occur because there is very small distance from the boundary. So that's why the distance has to be equal to at least 1.5 meters, 1.5 of diameters for rivets. And if they are bolts, for bolted connection, this distance is furthermore increased. This is distance from the edges, and also in between bolts or rivet, there has to be some amount of distance kept for so that the the parts that are being joined or that are joined do not fail. It is a simple example. You are not concerned in detail with this example, but it is only to show you what are the different type of stresses applied on a single joint. For example, it is an example of butt joint. You have one plate here, one plate here. You have two boards here and two boards here, two boards here, and you have applied external load F. They have also given the grade of bolt, they have given the diameter of bolt, they have given the thickness of plate, and also they have given the width of plate. The width of plate is also given. All the things are given, and also distances are given. They have asked us to calculate F. How to calculate F? We need to calculate F by applying all the loads. We need to calculate when the bolts are in shear, how much F it can support before failure, how much force member can support before failure, how much force they can support when in how to say, axial shear. All the things in all the for all the stress cases, we have to calculate safe value of F, and then factor of safety they have already given us, and the value of F which is least for all the cases will be considered as safe value of F. For example, for the first part, the bearing in bolt, and what was bearing? The bearing was compression at this was bearing. So what was the area for bearing? I have already told you that if this is the applied stress, first of all, for bolt, the safe strength is SP, and for members, it is SY. In the problem, they have given us that it is 1040, 1018 cold rolled steel. So you can just check for the value of FSY. I have written the value. I will just show you what is the value. For this 1018 cold steel, for example, 8-6, sorry, 8-6, for 1018 cold rolled steel, the value of SY is equal to 54 kpsi, and similarly S ultimate, if required, is equal to 64 kpsi. Similarly for bolt, what is bolt? What bolt we are using? It is grade 5 SAE grade 5 bolt. So for that word, we can just check value of SP comes out to be 85 kpsi, and value of S ultimate from table 8-9, this value comes out to be 120 kpsi. So these values can be taken. These are material property. Now just go to this. We have the value of SP. Factor of safety is design factor of safety was 1.5. Sigma is equal to sigma is equal to SP by ND. And what is sigma? Sigma is equal to F divided by 2 into TD. What? Why 2? Because we have two rivets or two bolts. So from this equation, F is equal to 2 TD SP divided by ND. All the values are given. So we substitute values and we will get F is equal to 85. Similarly, for members, equation is same. Equation is same because steering area is this. Bearing area is this for members. This is the bearing area. Similarly, this is the bearing area and this is the bearing area. So dia into depth, which is T in this case. 3 by sorry sorry for this plate, because we are talking about this member. So this plate, this is a 4 area, so we will get 1 into 3 by 4, which is dia of bolt. All the equations are same, so we'll get 54 kip. In simple words, when we apply force at 54 kip, bearing limit of bolts is reached. Bearing stress of member is reached, and for bolt 85 at 85 kip, bearing strength of bolts are reached. So bolt will remain safe, members will fall far below 85 kip. So the for with reference to bearing stress, the safe load is 54 kip. We will calculate F with reference to shear in bolt and shear in plane. For shearing force, for each bolt we have F by 4 force, because total force is 4. 4 divided by F divided by 4 gives us force on one bolt, or in here they have calculated F divided by 4 into area, which is equal to pi by 4 d square, area of one bolt. So this will be the shearing area, and this is the shearing force. Force divided by area gives us shearing stress on one bolt. This is a shearing stress on one bolt equal to tau. SP, this is proof strength in case of axial loading. Why we have multiplied 0.577? You will study in MOM 2 that if you have value of SY and you need to calculate SSY, yield strength in shear, so you have to multiply SY equal with 0.577. That's why, because yield strength, or in case of this we have yield strength or proof strength was given in terms of normal stress. So for shear we need to multiply it with 0.577. So we have, once we have value of this, SP is given, we have all the values, so we can calculate value of 57.5. At this value, the bolt will fail in shear. The one cross section of bolt will slide on another cross section. Similarly, in shear plane, in case of threads, because thread area is a little bit small, it is like this. This is outer area and this is thread area. In this case, they have taken solid in between. This is a total bolt outer area, this is inner area, and this is the minimum area of the bolt. So AR is taken with reference to the bolt which was 3 by 4 inch. For 3 by 4 inch, take the value of AR, so this will be the minimum area. For this minimum area, they have calculated the value of F, which is equal to 45.9. Logically, also this larger area will have smaller stress and it can support much more load than this smaller area. So at this value, the bolt will shear, the threaded portion of bolt can be sheared. We don't know which area will be sheared, but we need to calculate all the with reference to all the stresses, we need to calculate minimum amount of force. If we go in the detail of shearing, edge shearing, what is edge shearing? just for here. If this area is from this point, to this point, this length is small, there is a rectangular area, this length multiplied by its width. Similarly, at this point as well, we have this area, one area and two area. What is its value? Thickness, which is equal to this half inch, multiplied by this area can fail here, or it can be failed that this inner plate can be failed here, two times of area. If this area is small, this whole slice, due to shearing, this slice will come out like a slice of cake. So what will be the shear area of this slice? If this slice comes out, let's say this slice comes out of this area, the shear area will be one this and one this back area. And how it will calculate it is the height or thickness, and this is the distance from the edge. In this case, it is written 1.5 for this and 1.5 inch for this material as well. So if this fails, the area is 1.5 inch multiplied by thickness, which is half inch, and for this 1.5 inch this distance multiplied by thickness, which is 1 inch. So you can calculate this value for all. Here they have only calculated for this plate, not the supporting plates. For this plate, for this area, this value comes out to be 93.5 kip. It means that at 93.5 kip of external force, there is a possibility of shearing of members at this plate. Similarly, tensile yielding. There is also a possibility that this material fails in tensile load. How? If you just do not consider this pink portion, there is a gray plate below. The cross-section area of this plate is this thickness multiplied by its width. This cross-section area, which is equal to 4 minus 2 bolts multiplied by dia. So it is a cross-section like this cross-section minus this area minus these are 2 bolts, and this is the whole cross-section, which is thickness of plate, which is 1 inch, and this 4 minus 2 times dia will give you this cross-section area divided by factor of safety. Again, if you calculate at 90 kip, there is a possibility that this cross-section, this plate, this gray plate will fail in shear due to axial loading. And at the end, it is of no concern, but there is a possibility that this plate will also fail. For example, at this point, at this cross section, there is a possibility that this plate will also yield, and for this yielding, the area is this width multiplied by thickness, which is equal to 1 inch. So 4 into 1 is the area, and 54 is the strength, and we can at 145, and this is the highest load. It means that if at 144, for all the values that we have calculated, 144 was never being calculated. So all the other values are far less than 144 kip. So this is the value at 144 kip. This plate yields itself at this point, at any cross section. There is a possibility that this plate yields. So this is the maximum force calculated. It is the method of calculating the stresses in the board. The next topic that I will be explaining in the coming video is eccentric loading. At the end of this slide, I am just explaining what is eccentric loading. Take this example. This is the example that I have already explained in the previous slides. The direction of it is a cantilever beam, and direction of beam is outside or inward to the screen. There was a component, shear component, and because the distance of each bolt from the loading is same, so the F divided by 4 force, 1/4 force will act on each bolt, or each bolt will resist 1/4 of a force. But if the case is like this, for example, the beam is in the same plane as the bolts. In this case, if the external load F is applied, these bolts 1 and 2, these bolts are nearer to the force and these bolts are further away from bolt. In other words, these two bolts will resist some other amount of moment, and these two will bolts some other amount of moment. We need to calculate how much force is resisted by each and every bolt, and from that there will be a component of force and there will be a component of moment resisted by this bolt. So we need to calculate uh, force plus force due which is resisted by moment, and the bolt which is resisting maximum amount of load, we need to design that bolt. The remaining bolts will be safe because on those bolts the force will be less as compared to this one bolt. So this is the case of eccentric loading. This is a short topic. We will be having I will be explaining the topic, and then one example and one problem will be solved and the chapter will be ended. So see you in the next video.